So now I'm going to show you how we can use the definition of a derivative to come up with the derivative of the following functions. We might not do all of those, but we'll do most. So, and I'm just going to warn you, you are probably going to hear a yippee border collie at some point during the video today. So what is that definition of the derivative again? And there are a couple of ways we can do it. So I'm going to do the one that gives us f prime of x, so the function version. Right, so this is the limit as h approaches 0, f of x plus h minus f of x over h. Right? So slope of the secant line, and we're taking the limit as h approaches 0. Difference quotient right there. And again, if you want a little picture, right, kind of keep it going, and I'm just going to do an x squared graph. The idea is, right, for some value x, you go out a little bit h from that, and then the slope of the secant line, you find your change in y value, f of x plus h minus f of x, and then the difference in the change in x value, right? So that is h between x and x plus h, the difference is h. Okay, so let's go ahead and do this for the constant function. So what does the constant function look like, right? So constant function. So f of x equals c, right? So here we go. We're going to do the definition. So f prime of x says we're going to take the limit as h goes to 0 of, so f of x plus h. Well, if f of x is the constant c, then it doesn't matter what you plug in, what you get out is c. Same thing for the right side. Minus f of x, well, f of x is c, and then that's over h. So the limit of, as h goes to 0, of 0 over h. Now the top is definitely 0. The denominator is just getting close to 0, right? So it doesn't actually have to get to 0, it just has to get close. So the top wins, and 0 in the numerator is 0. So this means the derivative of a constant function is 0. So another way you could think about that, think about it graphically. Right? So find some constant function. There's my c. And remember, the derivative tells you the slope of the tangent. Well, if my line is horizontal, all of my tangent lines are also going to be horizontal, and the slope of a horizontal line is 0. So that makes sense. So constant function. How about the identity function? So the identity function right, that's f of x equals x. So just think about what that should be if you think of it in terms of slope of the tangent line and what this graph looks like. Okay, so I want you to have kind of an idea, and then we're just going to walk through. We're going to do the limit of the difference quotient. Here we go. Limit. H approaches 0. So f of x plus h. So remember, f says whatever you give me, I'm giving you the same thing out. So if we give it x plus h, so that first part in the numerator is going to be x plus h minus f of x. F of x equals x. So minus x over h. And we tidy before we do our limit. So x plus h minus x, that's just an h over h. Tidy again, because we can. So we're taking the limit of 1 as h goes to 0. Okay, well the limit of a constant is just the constant. Okay, so the derivative of the line, right, so this identity function, that's the line y equals x. Slope is 1. Y-intercept is the origin, right? So the slope of all your tangents, also 1. Same as the slope of the line. How about the squaring function? Let's scoot this camera down just, oh, nope, looks like I've got to scoot up. I've got a bright light behind me. Okay, squaring function. you want to pause and try this one on your own, I bet you can. So limit of f of x plus h squared minus f of x, there's our squared, over h, and we're letting h go to 0. So be careful. I was noticing some folks are still squaring your binomial by just squaring the terms. Remember, that's an expansion. So you can write it out in FOIL, or if you know the pattern, x squared plus 2xh plus h squared. So what do we have then? Limit h approaches 0, x squared plus 2xh plus h squared minus x squared all over h. So the x squares, I have a positive and a negative, so those are gone. So it looks like we're doing the limit as h goes to 0. What do we have up there? 2xh plus h squared over h. So cancel an h because everybody has one to give. And now we can do the limit. H goes to 0. 2x plus h. Right. I didn't plug it in up here, right, and the next to the last step because I would have gotten 0 over 0. So I wanted to simplify first, and now I'm going to go ahead and plug in. So the h goes to 0, so the limit is 2x. So what does that mean? It means if f of x equals x squared, its derivative, so f prime of x, is 2x. Okay, I'm going to grab a new sheet of paper. Let's skip cubing because I'm going to do a more generic one here in a bit. Let's go ahead and do the reciprocal function. So the reciprocal function f of x equals 1 over x. So again, we're trying to find its derivative. So f prime of x equals the limit as x approaches 0. F of x plus h, so that's 1 over x plus h, minus f of x all over h. So again, I've been kind of skipping this step because I think we've done enough limits in the previous chapter, but we try to evaluate by just plugging it in by substitution. So if I plug a 0 in for my h, I have 1 over x minus 1 over x in the numerator, so that's 0. And in the denominator, I have 0, and 0 over 0 is still undefined. Right? We'll come up with some strategies later on in the quarter, but for now we just say undefined, so we can't do it. So instead, we do some manipulations on our function. Hopefully we get to something that we can evaluate. Complex fraction, remember the strategy is just to tidy it up. I'm going to do that by multiplying top and bottom by the common denominator. So x times x plus h, 1 for the top. Same thing for the bottom. On the top, it's going to distribute. So we're taking the limit as h approaches 0, So as it distributes, so when it multiplies the left fraction, the x plus h's cancel, and we just get the x. When it multiplies the second fraction on the top, the x's will cancel, so we'll get minus the whole thing. So minus the x and minus the h. And then the denominator, we have h times x plus h. And then we tidy. So limit h goes to 0. So the x minus x are gone, and I just have a minus h on the top. On the bottom, I have an h times an x plus h. Okay, that's cool. So I have an h that's a factor on top, h that's a factor on the bottom. It's this one out in front that's timesing the rest of it, not the one inside, because that's attached with a plus to something else. So cancel those two h's. Be sure to leave behind a 1 for the top, in this case negative 1. 2 steps from done because I'm just writing out lots of extra stuff. So negative 1 over x times x plus h. Now I can evaluate the limit by, right, substitution. Plug in your 0. So I'm going to have negative 1 over x squared. So the limit, oh, I guess that's it, equals negative 1 over x squared. So again, if f of x is 1 over x, its derivative is negative 1 over x squared. Okay, so let's just do 2 more. We'll do the square root function. I think I can fit it all on this page here. So, right, f of x equals square root of x. So f prime is defined to be the limit h approaches 0, f of x plus h minus f of x over h. So what was our strategy when we had radicals in our difference quotient? We multiply top and bottom by the conjugate. So conjugate, same 2 terms, you change the sign in the middle, right, between the 2 radicals or between the radical and non-radical. So that'll be an x plus h, right? So they stay the same. The 2 terms stay the same, but you change the sign in the middle. So in this case, it'll be a plus. And then just so that we're not changing its value, I multiply the bottom by the same amount. So, right, this is just our very convoluted way to write the number 1. Same thing top and bottom. Right? And then the pattern we use when you multiply 2 conjugates, right, the outer and inner, right, have the same value but different signs, so those always go away. So this is the time where we get the first one squared minus, because you're going to have a plus and a minus, the last one squared. So x plus h, when you multiply square root x plus h times square root x plus h, okay, then minus square root x times square root of x, that's just an x. Then our bottom got a lot uglier, so that's h times all of this. I'm just going to go ahead and write that out. So h times the quantity square root x plus h plus square root x, okay? Tidy the top. Limit h goes to 0. What do I have? X minus x, so those guys will go. I'm just left with the h on top. I have the h out in front. Then I have my radical. X plus h. There's the border collie I told you you'd expect. Cancel your h's. Leave behind a 1. Okay, I'm ready to take my limit. In fact, let's just go ahead and do it here. Let's plug in our 0. So the 0 for the h, right, wipes out this h on the inside. So now I have 1 over square root x plus square root x. So a square root x plus another square root x is 1 over 2 square root x's. And that is the derivative. So again, if f of x is square root x, its derivative, f prime of x, is 1 over 2 square roots of x. Okay, so the last one I want to do is a generic x to the n. So f of x equals x to the n. So one thing you have to know before we can do this, and that is the expansion, so binomial expansion formula. And essentially it's if you have x plus h to the nth power. Doesn't matter what, we'll say n is a natural number. What you get is n, sorry, I started thinking instead of writing. You get x to the n plus n x to the n minus 1 times h plus some other coefficient, don't really care what, I'll say a c, x to the n minus 2 h squared plus, and then you have however many terms you need, and then your last term is going to be h to the n. Okay. Well, what I need you to notice about this is that, okay, the first term does not have an h in it. The next one has an h to the first, every other term is going to have h to a power 2 or bigger. Okay, so keep that in your head. Here we go. We're going to find our general formula. So we're going to take the limit as h goes to 0, x plus h to the n minus x to the n all over h. So again, if we expand our binomial, right, we're going to get x to the n plus n x to the n minus 1 h plus some constant, I don't know, I'm just expanding this guy out, x to the n minus 2 h squared plus a bunch of stuff plus my final term for expanding this guy, h to the n. So that's all that, okay? And now we have to subtract off x to the n. And we're dividing by h. Okay, look what happens. So I have an x to the n and a minus x to the n. So those guys are going to cancel. Limit h, my h's are trying to be n's. Limit as h goes to 0. Who's left up on the top? Right, I have n x to the n minus 1 times h plus c x to the n minus 2 h squared plus all those other terms with h's in them plus my final h term, h to the n, and that's divided by h. So every term in the top has an h to donate, right, to cancel with this h in the bottom. So I can cancel the h in the bottom, and it gets rid of, right, the h from my first term. It gets rid of one of these, so that'll be an h to the first. Every other term is still going to have an h in it, and that last one will be h to the n minus 1. So I'm taking the limit as h goes to 0. I'm almost done. It's worth it, I promise. I have n x to the n minus 1 plus c x to the n minus 2h plus all those other terms with constants and x's and h's until I get to my last term, h to the n minus 1. I don't have a denominator. I can evaluate by plugging in h equals 0. Plugging in h equals 0 wipes out all of those terms except for the first one. So the derivative is that first term. So if f of x equals x to the n, then its derivative, f prime of x, is n x to the n minus 1. This is actually, I think it's called the power rule, and it lets us take the derivative. So notice what happened. Power comes down in front, and then you take away 1. So you can check with the other ones that we did already and see if that held true. Would the power rule work for those derivatives that we found the long way?